Hi everyone, welcome to this talk about linear coupling of gradient and mirror descent. My name is Yuan. This is a joint work with Lorenzo Arecchia, who is now moving from MIT to Boston University. So linear coupling is going to be a very powerful technique, and today, as a special focus, I'm going to provide a novel and simple construction of the accelerated gradient method using this linear coupling. All right, so because both gradient and mirror descent methods are first-order methods, let me first remind you what the setup is for any first-order method. Suppose we're minimizing some function fx, where f is convex, and for simplicity of today's talk, I'm assuming that f also to be differentiable, and x is an n-dimensional vector that is totally unrestricted. In general, like x can be restricted to be inside any convex set, but I'm going to remove that assumption to make my notation simpler. Suppose this is function f, and I want to denote by x star the minimizer of the function. Now, first-order methods are those type of algorithms that at any point, say x on this curve, they're only allowed to make queries and compute the first-order gradient of the function, but not to say the Hessian, second-order derivatives, or even higher third or fourth-order derivatives of the function. And the goal of any first-order method is to minimize the number of such query points x1 through xt in order to ensure that at the very end, they can output some point, say xopt, whose objective difference to optimal is at most epsilon. So this is also known as epsilon additive approximate solution. So I am personally very interested in first-order methods, especially because such a limited way of accessing the function really makes sure that the algorithm can run very fast and often in nearly linear time. So, of course, whenever I write this gradient notation, I mean full gradient of the objective, and many of the things I'm going to talk about today also works for stochastic or even stochastic coordinate gradients. But I'm only going to focus on full gradient just to make all the notations as simple as possible. Now let me also remind you about what gradient and mirror descent are. So gradient descent is a type of method that is typically analyzed under the assumption that the function f is smooth. In other words, between any 2 points x and y, the difference between the gradient at x and y in terms of some dual norm denoted by this asterisk is less or equal to L times the distance between x and y measured in the primal norm. So here the primal norm could be the 2 norm, and if so, the dual norm or the gradient, the norm on the gradient is also 2 norm. And if the primal norm is 1, then the dual norm will be infinity, and so on and so forth. So the key idea of gradient descent is really very simple. At any point, say x1 of the function, it tries its very best to decrease the objective as much as possible. So it keeps decreasing until it reaches like an approximate minimizer of the function. So this idea is very different from its counterpart, the mirror descent method. So remember that at any point, say x1, we can compute the gradient, and the gradient basically means a linear lower bounding hyperplane to the objectives. At x2, we can have a different linear lower bounding hyperplane. So the key idea of mirror descent, or depending on which subcommunity one comes from, one may also call it follow the regularized leader or dual averaging. So the key idea of any of these methods are to basically intelligently construct a sequence of points so as to hope that the average gradient of these linear lower bounding hyperplane, which by the way is another linear lower bounding hyperplane to the function because it's a linear average. So those methods are hoping that the average, typically the uniform average of those hyperplanes, becomes as flat as possible. And one can actually turn this into a very rigorous analysis and show that the flatter this linear lower bounding hyperplane is, then the closer one can construct a point that's close to the minimizer. Okay, So here is a quick sum up about mirror descent and gradient descent. So for mirror descent, if we keep receiving small gradients, then it's very easy to see that the average of those hyperplanes are very flat. Okay, but if we keep receiving large gradients, in other words, like if we keep receiving steep gradients, then it's much harder to obtain an average, which is very flat. One can actually turn this into very rigorous proof, but I want to summarize this personally as saying that having small gradient is equivalent to having faster convergence for mirror descent type of method. This is in contrast to gradient descent. Remember that gradient descent decreases the objective at every single iteration. And therefore, if one receives a large gradient, he can decrease the objective, typically larger. And if he receives a smaller one, he can decrease it maybe a bit smaller. So therefore, I want to summarize gradient descent type of method as basically those methods that converge fast whenever they receive large gradients. So now, like by basically staring at this picture, a natural question arises. That is, can we combine gradient and mirror descent to produce a much faster algorithm? The answer turns out to be yes. This is what we call the linear coupling technique of gradient and mirror descent. Because one cannot talk about the convergence rate with respect to an abstract function in the air. So therefore, for today's talk, I want to really focus on a special class of functions. That is, again, the class of smooth objectives. Remember that I defined 2 slides ago of smooth functions to be the ones that whose gradients between, say, x and y do not change too much if x and y are close to each other with respect to some parameter, say a constant L. And also recall that gradient descent is typically analyzed with respect to smooth functions. And by the way, the convergence rate of gradient descent turns out to be 1 over epsilon. That is, if one wants to achieve an epsilon additive approximation, then the number of iterations needed is proportional to 1 over epsilon. But this turns out not to be the optimal one. The optimal one is the so-called, for this class, the optimal solution, the optimal first-order method turns out to be the accelerated gradient method, whose convergence rate is quadratically faster, at the magnitude of 1 over square root epsilon. And this was very originally discovered by Nesterov back to 31 years ago. So for those of you who remember Nesterov's method, this is a snapshot of one of the pages from Nesterov's textbook. So his method has many mysterious components, such as like choosing this parameter to be like the root of a quadratic function and the several linear summations that are a priori like not clear why they are here. And for many researchers, actually, they have regarded Nesterov's method as an algebraic trick. And but I personally view it as an interesting Gaussian knot. In other words, like it's a very beautiful, very elegant knot if you have seen it like in person. But unfortunately, it's very hard to unravel it. In the rest of the talk, I'm going to use linear coupling of gradient and mirror descent, basically to produce a method that has the same convergence rate as Nesterov's original method. Let me first illustrate this by the following thought experiment. Remember that our objective is smooth in today's talk, and without loss of generality, let me assume in addition that we start from a point x0 whose distance to optimal is at most 2 epsilon. And I only want to be epsilon away from optimal. In other words, I'm like 10 meters away from the destination, and I only want to be 5 meters away. So this last stage of the method turns out to be the heaviest component of nearly all first-order methods. And therefore, it really suffices for me to analyze this stage. Okay. So therefore, this first assumption is like really a without loss of generality. But the second assumption is really the one that I want to assume for this thought experiment. That is, suppose the gradient that I receive in terms of its dual norm is either always large or always small, with respect to some parameter k that I can even control. Of course, in reality, like the gradient may be sometimes larger and sometimes smaller, but for this thought experiment only, I'm going to assume that it's either always larger than or equal to k or always smaller than or equal to k. If it is the former case, let me state that I want to perform T1 steps of gradient descent. In particular, one can actually do the analysis and see that every single step of gradient descent decreases the objective by at least k squared, if the gradient is at least of size k. And therefore, in order to make a total progress of epsilon, T1 only needs to be epsilon over k squared, in order for me to decrease the objective consecutively by at least a total amount of epsilon. So if it is the latter step, the latter case, that is all the gradients are smaller than or equal to k, then I claim that I want to do T2 steps of mirror descent. Again, like ignoring the analysis, one can actually show that the number of steps needed is k squared over epsilon squared in this case. And finally, by just staring at this T1 and T2 two formulas, it's very easy to see that if one picks the best and the magic parameter k to be the value that ensures T1 equals to T2, then this total number of iterations, T1 and T2, which is equal to 1 over square root epsilon. Okay, so this matches the best known convergence rate of Nesterov's method or accelerated gradient descent method. So let's now really see how we can turn this thought experiment into a real algorithm. So at any iteration k, suppose we're at point xk, remember that if we receive large gradients, we can perform gradient steps, and if we receive small gradients, we can perform mirror steps. And the difficulty now arises because in reality, we may sometimes receive large gradients and sometimes receive small gradients. In fact, if we keep receiving large gradients, remember from the previous slide, we can keep decreasing the objective. All right? But in fact, gradient and mirror steps have to be executed consecutively. Let me illustrate this. Here is a very naive and simple attack that does not work. Suppose that whenever we receive large gradients, we perform like a gradient step. Whenever we receive like small gradients, we perform a mirror step. And now like this alternative applications of gradient and mirror step may completely destroy the algorithm. For instance, we may not necessarily decrease the objective. So remember that mirror descent is in fact a type of dual method that really works in the gradient space. And therefore, mirror descent may not necessarily decrease the objective. And by the way, mirror descent may very often increase the objective. In such a case, if we alternatively have gradient and mirror steps, then we do not necessarily decrease the objective, right? And there's actually a similar picture for mirror descent, which I don't need to illustrate today. So here is the actual algorithm, and also the simple fix to the dilemma on the previous slide, which is the following. At any iteration, let me perform two steps, both the gradient and the mirror step, regardless of the size of the gradient, and then choose to use a linear combination of the two. In other words, this is like a mixed strategy in game theory that avoids any of the worst possible scenario to happen. And this parameter alpha is going to be determined to be the best trading parameter that balances the two steps, just like the parameter k in the thought experiment. So I'm not going to show you the detailed analysis, which is going to be very simple. It's a very simple combination of the convergence analysis of gradient descent and mirror descent. But I want to state that this simple idea just recovers Nesterov's method. In other words, it provides the correct 1 over square root epsilon convergence rate, and its method is slightly different from one of the versions of Nesterov's method, but it has the same convergence rate. And at this moment, I want to really declare that this Gaussian knot is unraveled. In fact, what is very exciting about this linear coupling technique is that it can go way beyond Nesterov's method or accelerated gradient method. So let me illustrate this. Remember that in the theory of optimization community, here is how most of the papers are written. So the authors begin by defining or recalling a class of functions, for instance, the class of smooth convex functions or the class of, say, proximal smooth functions and so on and so forth, and then try their very best to obtain the optimal method for that class. So these works are very beautiful, but I want to state that in reality, here is a different type of problem that we face in, for instance, the theory of computation, machine learning, or operations research communities. In particular, we may be interested in, say, optimizing a packing problem, a scheduling problem, or a max flow problem. And one classical approach of connecting these two words is to basically turn this arrow up. In other words, to reduce the objective below to one of the classes above, and then to apply the optimal method above, such as Nesterov's method, to solve these problems. But this path may not be as efficient as it looks. For instance, many of the problems below, if one tries its very best, it cannot be like reduced into one of the classes above. For instance, many of the objectives below may not be smooth by nature. And even if one uses, say, Nesterov's smoothing technique to force those objectives to be smooth, still, like, there is some loss in this way, right? But perhaps more importantly, even if some objective below falls into one of the categories, such as like smooth functions, however, using the optimal method for a much larger class of functions to solve a smaller individual problem that belongs to this class, then the ultimate algorithm may not be optimal anymore, right? And therefore, I propose, and I am personally very interested in the other totally different approach of connecting these two communities, which is to turn the other arrow downside. For instance, in today's talk, I have abstracted away this very interesting linear coupling technique from basically the theory of optimization. But I want to say that it's a very general technique that we can borrow and solve individual problems below. Here is one example, and in fact, a very crucial example. That is the so-called packing LP, packing linear programming. Suppose that we want to maximize 1 transpose x, subtract to the constraint that is ax is less than or equal to 1 in the vector sense, so coordinate wisely, and x being a non-negative vector. So this program is called a packing linear program because each entry of the matrix A is required to be non-negative. So at this moment, it's very easy to see that we can basically regard each coordinate of x as the amount of product we want to produce for, say, the ith product. And now the constraint ax less than or equal to 1 can be understood as the restriction. For instance, its first row can be understood as, say, the total amount of, say, electricity that one consumes cannot be larger than or equal to 1 unit. So of course, like, packing linear programming is very important. For instance, like bipartite matching and certain classes of routing problems can be written in this form, in this packing linear programming form. And the packing linear programming can also be solved in nearly linear time. That is proportional to big N, the number of non-zero entries in this matrix, and inversely proportional to epsilon, the approximation factor, to some constant cth power. So before our work, back to actually 21 years ago, there have already existing algorithms that can achieve C equals to 4 for parallel algorithms, and for sequential ones, they can achieve C equal to 2, also back to roughly 20 years ago. And in our two separate work, we managed to improve the first one into 3 and the second one into 1, both using this linear coupling technique. On the next slide, I'm going to illustrate how we managed to obtain so by some very simple high-level description. That is, we first reduce this linear programming into a purely minimization problem. That is, it suffices for us to minimize some convex function f. But unfortunately, this f is not smooth, and therefore one cannot apply the Nesterov method below. And by the way, even if one uses some smoothing technique, he will get an algorithm that runs very, very slow. So instead, we do the following. In these two separate papers, we express the gradient of function f as a summation of two components, one denoted by Cc and one denoted by eta. And it turns out that for packing linear programming, Cc can be, one can assume that Cc is between -1 and 1, and eta is between 0 and infinity. In other words, we call this the gradient truncation technique that allows us to truncate the possibly large gradient into its small and large components, Cc and eta. And then we basically perform gradient descent on eta and mirror descent on Cc. Using linear coupling, we can obtain a simple 1/epsilon³ convergence rate for parallel algorithms. And for sequential ones, life is actually much more involved. And we basically perform gradient descent on this large component eta, but we perform both gradient and mirror descent, although they are coordinate version, to this Cc component. And then somehow using linear coupling of these 3 different first-order methods, we obtain a 1/epsilon convergence rate for sequential algorithms. So of course, on this slide, I'm only waving my hand. And in practice, we're really using a lot of more techniques in addition to linear coupling. But linear coupling is really staying at the center of these two separate results. So my personal conclusion here is that we can now, at this moment, really unravel this Gordian knot by expressing not only Nesterov's method as a component, as a linear combination of gradient and mirror descent, but in fact, we can use this insight. That is, gradient and mirror descent are two different components for first-order methods to design more and more fast first-order iterative algorithms. So having this view of gradient and mirror descent really have their complementary performances, and one can combine them. Now, one can not only combine them, but also even to reconfigure the picture. That is to design different gradient descent and different mirror descent, and even more than one on either side, and then to linearly combine the methods to provide even faster convergence rate for each individual problem at hand. So it's going to be a very powerful technique, and I believe more results will come in this line of research. So thank you very much for listening, and our paper can be found on this QR code. Bye-bye.